more projects to pursue?
I work with the Federal Aviation Administration in Atlantic City, New Jersey. That's where we have our William J. Hughes Technical Center. So in this presentation, I'll try to give you some information about who we are, what we do, and what kind of projects we are doing. So this is just some numbers, some statistics about air transportation system. Over 600 million passengers annually at about 13,000 airports. Now the NIPIAS has identified 3,400 airports as being significant for the nation's air transport system, and these airports are eligible to receive funds from Airport Improvement Program, the AIP. AIP grant, 28%. It's about $3 to $4 billion a year program, and our research money at Tech Center comes from this AIP program because the work that we do ultimately goes towards improving airport pavements. FAA's Office of Airports, ARP1 in Washington, D.C., maintains all the advisory circulars. So any project that is using AIP funding has to follow FAA standards and specifications. And there are cases where you will deviate from those standards. In that case, you have to submit modification to the standards to FAA headquarters, and they'll look at all the documentation and whatever information you can provide, and then approve the project. So in Atlantic City, we run 2 full-scale test facilities, and we need to go back into a little bit of history. Full-scale testing for airport pavements is nothing new. It started in 1940s during World War II. And there were these big bombers, B-36 and B-29, that had wheel loads of about 100,000 pounds. So when you're looking at your truck traffic on highways, you're looking at maybe 10 to 15,000 pound wheel loads. Here you're looking at 100,000 pounds. And they wanted to see how these pavements would perform under this kind of loading. And the first series of test sections were constructed in Stockton, California, and US Army Corps of Engineers did most of the research work. And after that, from 1940s till 1970s, most of the research for airport pavements was performed by US Army Corps of Engineers. They have Waterways Experiment Station in Vicksburg, Mississippi. And these are some of the load cards that they use to collect performance data under different loading gear, landing gear geometries, and wheel loads. All the data and results that were collected during this 30-year period formed the basis of airport pavement thickness design procedures for the Federal Aviation Administration and also for the tri-services. And I don't know if you remember, but FAA design procedure had these nomographs where you would go and get thickness of different layers. And these were all based on CBR design procedure. So they covered landing gears that were very simple, single wheel gears, to Boeing 747 that had four wheel gears. And the wheel loads for this aircraft was around 44,000 pounds per wheel. 2 6-wheel landing gears and then 2 4-wheel landing gears. And if you use existing design procedures to evaluate how the pavement would perform, you would need pretty significant thicknesses to prevent early failures. And an aircraft manufacturer cannot sell an aircraft if those aircrafts can't land on the airports. So Boeing invested some money and they did some research in Russia. But then if Boeing comes and says that our planes are no more damaging than what the previous generation planes were, no one is going to listen. So then FAA decided to set up a full-scale test facility in Atlantic City, New Jersey, where Boeing contributed $7 million for this facility. And again, the idea behind this facility was to collect performance data. So use a full-scale landing gear, compare the performance of the pavement under a 747 gear, which we knew was, the pavements were performing well, and then see how much life reduction would a 6-wheel landing gear cause. So that's our location, Atlantic City, New Jersey. That's where all of FAA's research takes place. It's called William J. Hughes Technical Center. And anything from air traffic control, firefighting, or payments, everything takes place in Atlantic City. And our sponsor is AAS 100. These are the people who maintain all the FAA standards and specifications and also make sure that they are being followed. And our part is to do the research and provide information for development of those advisory circulars. Our branch is called Airport Technology R&D Branch. Dr. Michelle Hovan is the branch manager. And our branch has two teams. One deals with payments and the other one deals with safety. So safety branch looks into lighting, airport runway markings, firefighting, and all those aspects. And our team, payments, does work in payment materials and structural design. And then we have a support contractor that provides us research support, and it's generally awarded on a 5-year basis. And then we work with different universities, consultants, and also US Army Corps of Engineers under a interagency agreement. And we also provide industry support for doing workshops, airport payment design workshops, payment evaluation workshops, and these are some of the organizations with whom we work on a regular basis. And then International Civil Aviation Organization also asks us to conduct workshops in different parts of the world because most of the countries are using the payment thickness design software that FAA has developed. Then we also work with a lot of universities because I think universities are the best place to do basic research in materials and stuff. And here's a list of universities that we are working with through research grants. So that is just a little bit about us. And now I'll go into the details of the two test facilities that we have. A test bed that is 900 feet long and 60 feet wide. And we have this machine that weighs 1.2 million pounds that is used for applying the wheel loads for full-scale testing. And there are two carriages that can be configured to any aircraft landing gear configuration and wheel loads. So if you're using 2 gears with 6 wheels each, we can apply a maximum of 75,000 pounds per wheel. And if you look at the current commercial aircraft fleet, the maximum wheel loads are about 62 to 63,000 pounds. And we apply Wander. These carriages move because even though the pilot tries to put his nose wheel gear on the center line, you still see some deviation. And we have done studies at taxiway deviation, and we have developed a Wander pattern that we use in our testing. And the machine works in a way so that if your test section fails, you can lift the gear and land the following test sections. Each test section is typically about 60 to 75 feet long. And then we have sensors that are embedded in these pavements, and we collect data, look at how the pavement is performing during testing. We can move the gears close to each other to look at gear proximity effects on pavement performance. And all the research that has been done there was used for updating the failure models for both concrete pavements and asphalt pavements. And that has been incorporated in a thickness design procedure called FARfield. And this is the current FAA standard for thickness design. You can download this software from FAA's website, and it's all free. And then things again changed about 4 or 5 years ago, because the current objective of the aircraft manufacturers is to increase the range of the planes and fly efficiently. So, which means more fuel, more range relates to more fuel. And one of the things they don't want to do is change the design of the wheel well, where your landing gear goes in, because any change in the wheel well reduces the payload capacity. So which means your wheel loads go up and your tire pressures goes up. So in these aircraft, this is the A350 from Airbus. And that's the Dreamliner. And then if Boeing also came up with 747-800, which was the extended version. And the tire pressures in these aircraft are reaching almost 250 psi. The old limit for tire pressure for X category aircraft was 214 psi. So that's a 40 psi increase in the tire pressure. And we don't know how this increase in tire pressure is going to affect asphalt pavement performance, because generally on concrete pavements, tire pressure does not have any significant effect. It's the whole gear load. But for asphalt pavements, tire pressure is a big thing. And with our current facility, we could not test at higher pavement temperatures because, as you know, most of the problems occur in asphalt when the temperatures are much higher, rutting issues and stuff. And the way our old facility was designed, since the whole machine moves back and forth, there was no way we could heat the pavement, and it's an indoor facility. So to collect performance data under aircraft wheel load and high tire pressures, we built a new facility which is called National Airport Pavement and Materials Research Center. And also, when you're looking at effect on the surface layer, the whole landing gear is not necessary, because the wheel load interaction that takes place at lower depths. So for evaluating surface layers, if you just single wheel is enough, as long as you can develop enough wheel loads and tire pressures. And here's a photograph of the new facility. So that's the machine or a heavy vehicle simulator that is used for full-scale testing. And we have 4 test lanes outdoors, and there are 2 test lanes inside this fabric-covered roof. Here's another view. These are our test lanes. So we have 4 lanes. These are constructed with different materials. And this is where the data acquisition system is located. And there are sensors embedded in the pavement. And all these connect to these handholds. And then there are trunk lines running into the data acquisition system. And that's our old facility, the National Airport Pavement Test Facility. So in that facility, we are doing research for looking at failures in the lower layers in the pavement structure. And in the new facility, we have designed pavement so that all the distresses are limited to the surface layer. Here's a view of the inside test lanes. There are 2 test lanes. And this is the test vehicle, and we have environmental chamber, and there are heaters. So we can set the test temperature, and there is an automatic control system that changes the power in each of these panels so that the temperature of the pavement rises uniformly. And this whole machine can be operated using a remote control for moving from one test section to the other. And the total weight of this equipment is about 300,000 pounds, which is a fully loaded Boeing 737. These are some of the specifications. We can apply up to 100,000 pound wheel load, so we have a lot of capacity available if the aircraft wheel loads go up. We can test with a single wheel gear. This is a 52-inch tire that is used on Airbus A380 and Boeing 777. And we also have a 2-wheel gear that can replace the single wheel gear, which is representative of a Boeing 737, which is the most common aircraft at most of the airports. Boeing 737 and Airbus A320. And we can apply wander in here, 6 feet wander width. And here's another photograph of relocating the machine from inside test lanes to the outside. So this is basically all the facilities that our pavements group owns. This is the National Airport Pavement Test Facility. We have a material testing laboratory. And then this is our material processing facility, and that's our new research facility. So now I'll talk about some research that has taken place at the National Airport Pavement Test Facility and what we are doing currently. This is the layout of the section. So we have 900 feet long test area. The subgrade is something that we have brought from outside. So we have 300 feet of low strength subgrade, CBR of about 3 to 4, 300 feet of medium strength subgrade, CBR of about 7 to 8, and 300 feet long for high strength, CBR of about 20 to 30. And in our first construction cycle, we had 2 flexible pavements and 1 rigid pavement on each subgrade type. But now the low strength is used just for asphalt pavement testing. All the concrete pavement testing is done on the medium strength. And on high strength, we are doing research on reflective cracking in asphalt overlays over concrete pavements. This slide shows a typical construction cycle. The first step is to come up with a set of objectives. What do we want to learn? And once we know the objectives, then we do pavement thickness design and develop instrumentation layout, construct the pavements, and then we characterize what did we build, look at uniformity within a test section. And then we perform full-scale tests, and during full-scale tests, we monitor pavement performance through sensor responses and also by measuring surface profiles, rut depths, crack maps, etc. And once the pavements are failed, then we do forensic analysis where we'll go and cut transverse trenches and we'll look at the failure mechanism and also see how the material properties have changed from construction time to the failure. And the idea is once you understand your failure mechanism, you can design it better so that it doesn't happen in the field. Because typically, airports don't want to shut down a runway for rehabilitation because it's very expensive. To give you an example, John F. Kennedy Airport in New York, they were building their bay runway, which is about 14,000 feet long. And it handles about 54% of their total traffic. And most of the aircraft are the ones that are flying from Far East. So they asked their contractor to complete 10,000 feet portion of the runway in 120 days, because once you finish that 10,000 feet portion, they can start using it for landings and takeoffs. And if the contractor did not finish in 120 days, penalty was $300,000 an hour. So you can figure out how much it costs for an airport to shut down a runway. And contractor finished it in 120 days, got $5 million bonus. So we number our construction cycles, and typically construction cycles that are odd numbered, 1, 3, 5, 7, have all been flexible pavement test cycles. And currently, we are in construction cycle 7. So in the previous construction cycles, we collected data to improve our failure models. For construction cycle 7, we are looking at perpetual pavement designs, because the idea behind perpetual pavements is you avoid fatigue cracking in the bottom of the asphalt and rutting in the intermediate layers. So all your distresses are limited to top 2 to 3 inches so that you can come, mill the surface, and put an overlay. And that kind of work can be done with overnight closures, like it was going on at Newark International Airport. And we are looking at what is the threshold of these strains so that you don't get fatigue cracking and also limit rutting. And another thing is the fatigue model for asphalt concrete that was used in our thickness design procedure was based on research done in late 60s and 70s based on Huckelone and Klomp method. University of Illinois had developed a fatigue model based on the ratio of dissipated energy change, and that model has been incorporated in our design procedure. And we are using data from these test sections to sort of validate / refine that fatigue model. And also look at the strain distribution within the asphalt layer, because you need that kind of information for refining your 3D finite element models for analysis. And on the south side of these sections, we are looking at the overload criteria, because according to ICAO, which is the International Civil Aviation Organization, for flexible pavements, you can apply 5% overloads without causing any significant damage. And this was a number that was just picked out of with no scientific background behind it. So we are trying to develop a criteria that is more mechanistically based. So in construction cycle 7, we have these test sections. These 4 sections are perpetual pavements. We have thicknesses ranging from 8 inches to 15 inches. And we have used a polymer modified binder, PG76-22. And this is the control section, which is a conventional flexible pavement. Some sensors that we have installed in these pavements, H-bar strain gauges to look at asphalt strains, multiple depth deflectometers to characterize permanent deformation taking place in each of the component layers. And this is a new sensor that we have used, fiber optic strain plates. And these give you the whole strain field in the asphalt thickness. And then some pressure cells to look at subgrade stresses and stuff. This is a photograph of multiple depth reflectometer. Here's a MDD going in. And this is where all these potentiometers sit. And they tell us which layer is contributing to the total rutting. And this is the new sensor that we are using for the first time. This is a fiber optic strain plate. And this plate is installed after your pavement section is constructed. We come and make a saw cut, and then the plate goes in. And there are 24 sensors. There are 8 sensors close to the surface, and they measure the horizontal or the tensile strains close to the surface, because with the radial tires, what you see is a lot of top-down cracking. And that's what we'll try to relate these strain measurements to. And then there are 8 vertical fibers. They measure vertical strains, which is related to rutting. And then there are 8 horizontal fibers at the bottom to measure horizontal strains at the bottom, which is related to bottom-up fatigue cracking. Here's a photograph of the plate. And these are all the fibers that go in. Close-up of the fibers. So they measure very localized strains. The plates are not that expensive, but it's a data acquisition system that goes to read one plate. The data acquisition system is close to $90,000. Here's the photograph of data acquisition system, and here's the installation of the plate. And we did some response tests on these pavements, different speeds. As we know, asphalt concrete is a viscoelastic material, so speed has a big effect. Speed, different wheel loads, different gear configurations, and all the results that we are collecting from these strain plates will be used for refining 3D finite element models. We have a research grant with Rutgers University who is evaluating this. And then for traffic tests, we use 55,000-pound wheel load, 6-wheel landing gear. And we are measuring straight edge rut depth measurements, surface profiles, and then crack maps in the thicker pavement sections. That's the conventional flexible pavement. And then we have a test section that has asphalt stabilized drainable base layer. And more important for this study for us is the fatigue cracking, because that's the information we are looking to calibrate our fatigue model. And that's our conventional flexible section. You can see significant cracking. That's the 8-inch section. And then we have 10 and 12-inch sections with very minimum cracks, and that's the 15-inch section with no cracks at all. The section was designed for 30,000 passes. So this just summarizes what we have found on our construction cycle 7. And we are in the process of quantifying these cracks and also looking at the PCI values for all these sections. Then there are some other asphalt pavements related projects that we have done. And one is, it's called Operational Life of Airport Pavements. This was in like early 2000s. Concrete industry went to Congress and said concrete pavements are designed for 20 years and they last 30 years. So we should get 30-year credit in life cycle cost analysis. And this way they would be able to put more concrete. Because currently about 90% of the airport pavements use asphalt concrete. So Congress, US Congress gave that study to FAA to look at whether our design procedures meet the requirements for 20-year design life. And in this study, we looked at the distresses that were occurring at different airports, concrete pavements, asphalt pavements, large hubs, medium size, small airports. And we basically looked at the condition of the pavement at the end of design life, and we showed that if all the FAA standards and specifications are followed for thickness design, materials, and construction, the condition of asphalt pavement and concrete pavements are very similar at the end of their design life. And this is a report that you can download from FAA's website. Here's the report number. And it looks at what kind of distresses are more common in airport pavements for asphalt pavements and also for concrete pavements. And then the other study that was done was on P401 specification, which is FAA's specification for hot mix asphalt mix design. And P401 was based on Marshall mix design. And what we showed in this report was that airport pavements generally don't have any significant problems in terms of performance. So P401 has been performing very well. And one of the reasons is the material requirements under P401 were very similar to what SuperPave has. But if you look, it's very difficult to find contractors that have Marshall mix design equipment available in their labs anymore. So FAA wanted to develop specifications based on gyratory compactor. And we did this study, and there were 3 research groups that were involved. We had a study going on with US Army Corps of Engineers, our support contractor SRA that subcontracted Advanced Asphalt Technologies. And then there was a earmark in the Congress in our budget that resulted in Airport Asphalt Pavement Technology Program, AAPTP, that was run out of Auburn University. And there was a project under that AAPTP to come up with gyratory compactor-based specification. So if you look in our Advisory Circular 5370-10G, there is an option for using SuperPave methodology for mix design. And then for binders, there is a table that provides you what kind of binder to use. And basically what it says is that you go to LTPP bind or your state DOT specification and see what is the binder grade recommended for your state. That becomes the base binder grade. So if it's a general aviation airport where your wheel loads are less than 12,000 pounds, then you can use that binder. But if the wheel loads are about 12,500 but less than 100,000 pounds, or gear loads, then you bump up the grade by 1. And if the tire pressures are going to be more than 100 psi, you bump up it by 2 grades. And it provides you guidance, how you do it. And then some caveats added to it. They recommend not going to minus 16 or minus 10 grade because that will result in block cracking. And now I'll talk about the research that is taking place at our new facility. So the new facility was dedicated end of August last year. And after that, we have basically developed a plan of how research will take place at that facility. And basically, this table or this flowchart summarizes evaluation of new asphalt technologies for airfield pavements, because we don't have any performance data available on how warm mix asphalt, stone matrix asphalt, or if you have wrap in your mix, how the pavement would perform under aircraft wheel loads. So that's the basic objective. And we'll be building test sections with standard P401 because we know the performance is good. And then we compare performance of these other newer technologies with P401, because once we know they're performing same or better, then we can develop specifications for that. And that'll increase in the use of these technologies at airport pavements. So we'll be doing extensive laboratory testing, characterizing these materials, developing performance models, and then we'll do full-scale tests. And we know there is going to be some sort of shift factor between the lab performance models and the full-scale test results. But once you know what kind of shift factor is there, then you can predict more reliably how that pavement would perform at airport pavement. And we'll also try to collect information on asphalt mixes that are going on different airports and how they're performing. And for that thing, we'll be working with our headquarters staff because they are in touch with all the regional offices. And again, test cycle is very similar to what we had for NAPTF. Come up with objectives, do thickness design, characterize what you built, and then test under full-scale loading, and then look at the failure mechanism. So currently, we just started our test cycle 1. And in this test cycle, we are looking at the effect of material. So we are comparing performance of warm mix asphalt with hot mix asphalt. Effect of tire pressure. So we are testing one test area at 214 psi, which was the previous higher limit for tire pressure. And these test areas will be tested at 254 psi which is a new upper limit for the tire pressure for aircraft. And then we are looking at effect of binder type. We know polymer modified binders perform better, but we are trying to sort of quantify that performance. How much more life do you get? And that relates to one of the bullets that was shown by, actually it was asked as one of the things in your question, how do you add into life cycle cost analysis the better performance that you get out of modified binders? So we have 4 test lanes. We have PG76-22 and PG64-22 for the warm mix asphalt. And in this series, we used Evotherm as the additive. And then we have 2 hot mix asphalt with PG64-22 and 76-22. And then the 2 indoor lanes are made with PG76-22 because that's the binder grade that is most commonly used on a commercial airport. And then we have these intermediate test areas where we'll test at more realistic test conditions, because the tests that we are currently doing in these areas are at extreme conditions. So our pavement temperature is 120 degrees, 1 inch below the pavement surface. And we have a slow moving load. We are testing at 2 miles per hour. So that's an extreme condition to test these pavements at. And we're using 58,000 pound, actually 62,000 pound wheel loads. This is the pavement structure: 5-inch thick asphalt surface, 12-inch thick crushed stone base, 12-inch thick sub base, and this material is also 100% crushed. And then we have a subgrade with CBR of around 15. So this pavement structure is designed in such a way that failure does not occur in any of these layers, and all the rutting is limited to the asphalt surface. Here's a photograph of inside the HVS. These are the heater panels, and that's the total area that we are testing. We are applying a wander pattern, and here's an infrared camera photograph that shows that the temperature distribution within the asphalt layer is pretty uniform. Here's another photograph, and we are also measuring strains outside the traffic area, and there are some asphalt strain gauges and pressure cells that are embedded in the pavement surface. We have already failed 2 of the test areas. This figure here shows you the location of the test area. So this is PG64-22, and that's the photograph of the failed section. Our failure criteria was 1 inch of surface rut, and this pavement failed in 250 passes, and this was tested at 214 psi tire pressure. This is the section with warm mix asphalt. That's the location. Also made with PG64-22, but warm mix. And we saw identical performance between the 2. But one of the things is these sections were constructed in end of May. So they had been sitting there for a couple of months before we actually went on testing them. We just finished testing a section with PG76-22, hot mix asphalt. So if you look at the performance comparison between 64-22 and 76-22, 76-22 lasted about 4 times the life of PG64-22. So it failed around 1,000 passes. Then the research that we are doing at our test facility is that under certain climatic conditions and stuff. So we are also trying to develop a project like LTTP or LTPP, wherein you're looking at pavement performance under different climatic conditions. So we have a project that is called Field Instrumentation and Testing. And the objective of this project is to better understand the long-term performance and behavior of pavement under different aircraft and environmental conditions. And also, the current FAA design procedure, the only material property it uses for flexible pavements or asphalt pavements is the CBR of the subgrade. So we are trying to collect information on other test methods so that we can look at the shear strength and resilient modulus of these materials in field. And that's the part of the second part of this project, improved characterization of paving materials. We are also collecting asphalt samples from different airports, bringing it to our lab, and doing dynamic modulus, flow number tests, APA, and stuff. This is a photograph from John F. Kennedy Airport. We instrumented some concrete slabs. That's our data acquisition system. And we have instrumented installations at LaGuardia. And there was a project we started in 1994 at Denver International Airport. And then this is an asphalt pavement project that we are involved in. With the advent of Boeing 737-800, the tire pressures went up for this aircraft from 180 psi to about 220 psi. And there are a lot of airports all around the world that are seeing this kind of distress, which is slippage and shoving at high-speed exits. So as your aircraft is going from your runway to the taxiway at high-speed exit, you see these shapes, in your grooves. And Port Authority of New York and New Jersey wanted to see, like, if we can monitor when this kind of failure starts happening. So we went in and we instrumented this pavement. This was, I think, in 2012. And the concept was that if you put some asphalt strain gauges at the surface of the milled asphalt surface and at the bottom of the overlay, they're very close to each other. So as long as the two layers are properly bound, the nature of the strains in both these gauges should be very similar to each other, and also the magnitude. But once the slippage starts taking place, the nature of the strains would change, and also the magnitude. And one of the reasons why this failure shows up is because as the aircraft is turning, it's also braking. So that induces very high shear stresses in the asphalt layer. So here's a photograph. We installed these sensors. So these were installed on the surface of the milled surface and at the bottom of the asphalt overlay. And Port Authority took a lot of care to clean the milled surface properly because they have seen these failures before, worked on the aggregate geology, selected stones that are not prone to slippage and stuff. And here are some results from those strain gauges. This is after the pavement was constructed. So the two layers are working properly. And for tack code, they used PG64-22 knead binder as a tack code. And they took care that the coverage was good and stuff. So here you see the strains at the bottom of the asphalt layer and the top of milled surface, same nature, similar magnitudes. And then in summer of 2013, you can see that something is happening in the pavement layer. And then the nature of the strains changes. So when your layer delaminates, the bottom of the top layer would show you tensile strains instead of compressive. And that's what happened here. And once we saw that in the results, we called Port Authority. They sent their engineer to visually inspect the pavement, and they called back and said, yeah, we are seeing the slippage issues now. So I guess tack coat is one of the things where they can work with, better tack coat, better material, maybe, I don't know, maybe PG or modified binder as a tack coat. Because another thing, if you look at the finite element analysis, 2 to 3 inches is the depth where you see maximum shear stresses taking place in the pavement. As the previous speaker also showed in his analysis, there was a graph that showed very high tensile strains at 2-inch depth. These are some photographs from our material characterization project. We are using dynamic cone penetrometer to look at the strength change with depth. And this is a lightweight diffractometer. You can capture the stress hardening behavior of granular materials and stress softening behavior of cohesive soils. And it fits in the curve when you do your lab triaxial tests for stress dependency, that this provides you that kind of information. Here's another equipment called Portable Seismic Properties Analyzer. And this equipment can be used for characterizing unbound materials. And there is another setup that can be used for measuring modulus of the asphalt concrete and concrete layer. And as you can see, it's very convenient. You need one person connects to your laptop, and it's powered through your USB port. And then we have a material testing lab where we work with the equipment manufacturers, because most of the equipment has been developed based on the needs of highway industry. So we work with the manufacturer to have a lot more flexibility. Like for fatigue equipment, we can take the strain response that we are measuring in our strain gauges and use that strain time history in our fatigue equipment and apply those kind of load cycles. And then similar thing with our asphalt pavement analyzer. If you remember, asphalt pavement analyzer typically had 100 psi tire pressure. We work with the manufacturer, so in our version, we can apply 260 psi hose pressure, more representative of aircraft type loading, because we are looking at a simple performance test that you can do in a short amount of time and tell whether the material can be placed on an airport or not. So we did work with the US Army Corps of Engineers. They developed a set of P401 mixes, and some of these materials met P401 specifications, some did not, because we wanted to see what's the criteria that identifies which materials should not go on airport pavements. And these are the results from the test. So based on these results, we came up with a criteria that if a material develops less than 10 millimeters of rutting at 4,000 passes, that material is good enough to go on an airport pavement and would give you good performance. But any mix that experiences more than 10 millimeters of rutting by 4,000 passes is not good enough to go on an airport pavement. So the criteria was developed based on this data set. And then we also had another set of samples or mixes, and these were well-performing mixes. So these pavements have been on an airport for more than 20 years. And the criteria was sort of validated with that kind of results. And the findings from this study are published in a TRB paper. And then in France, Airbus was doing a study at their Toulouse test section at Toulouse Airport. And they were using 3 different mixes: a rut-prone mix, their standard airfield mix, and a material resistant to rutting. So we got some cores from France, and the criteria that we had developed from APA was able to identify this material had more than 10 millimeters of rutting at 4,000 passes, so wouldn't go on an airport pavement, and also accepted the other 2 materials. Some future research. We are looking at perpetual pavements, developing a criteria for that, allowable overload on flexible and rigid pavements. And we have built a test rig at our facility where we're looking at reflective cracking in HMA overlays, because this is one of the weak points in our design procedure, because currently we just use a crack propagation rate of 1 inch per year. And we know that's not good enough. So we are doing these tests in the test facility, and University of Illinois is doing finite element modeling using generalized finite element methods to come up with a procedure that can be installed within our design procedure. And also look at geosynthetics used in airport pavements. And for NAPMARC, the new facility, we are looking at evaluating more green technologies such as warm mix asphalt, recycled asphalt in hot mix, stone matrix asphalt, quantify the benefits of modified binders, and full depth reclamation or rehabilitation. And the idea is to develop performance models based on the lab tests, and develop performance models based on the full-scale tests, relate them, and also the information that we collect from our field projects, so that we can come up with a design procedure that can handle the aircraft traffic of today and tomorrow in a safe and efficient way. And this is a document that you can download from our website. This is a research plan for next 10 years, because what we found is, in order to keep good flow of research funding, if you tell the higher ups in Washington, D.C. what your plans are, what you want to accomplish, your funding improves. When we started this facility, our budget was $6 million a year in 1998. Now we are up to $30 million a year, about $15 million going towards payment research and $15 million for safety. So this is a high-level plan that tells what we are going to accomplish. And if you're interested at project level, what projects we have for payments that fulfills those requirements, there is another document which also you can download from our website. And with that, I end my presentation. So I'll be happy to answer any questions that you might have.
Do you have any questions for Dr. Garg? Very heavy stuff.
Thank you very much.